Hello everyone, and thank you for inviting me to present our work and also to share how machine translation works. So my name is Mārcis Pinnis, and I've been working at Tilde as a researcher since 2011. So I didn't start with machine translation at first. I did some other natural language processing tasks like part of speech tagging, named entity recognition, terminology extraction. But sometime around 2012, since then I've been focusing on machine translation. And since 2015, all the industry, we've moved towards neural machine translation, so neural network-based methods in machine translation. And today I'm going to share you how neural machine translation works. But I'm not going to start with neural machine translation at the beginning. That will come sometime at the second third of my presentation. So I'll start with an introduction of what machine translation is, for those of you who are not very familiar. I'll talk about methods that have been used for machine translation previously, so before 2015 and 16, and also a little bit about Tilde's activities on machine translation. And then we'll dig deep into neural machine translation. If you have any questions during the talk, don't be afraid to raise your hand or shout out that I'm talking in riddles. Please explain a bit more, because I usually talk to more technical audiences, programmers or natural language processing people. So if I'm explaining something in too technical terms, just raise your hand. And we'll finish off with an explanation, or I'll try to show you how we develop machine translation systems. Not just how the neural machine translation engines work, but how to get systems that can be used by people. So let's start with the introduction. So what is machine translation? This is probably a very obsolete slide already. Most of you probably already know or have used machine translation systems like Google Translate or Bing Translate or Yandex Translate or our own Tilde's machine translation systems. So an MT system is a system that automatically translates text from one language into another language. And here you see an example of 4 machine translation systems publicly available that translate text from English into Latvian. These are actually the only public systems that translate from English into Latvian. So I haven't had the chance to find another competitive system that provides such features. Before we dig into the world of machine translation and the methods, I'll show you a video from 1960. It shows how people perceived the complexity of machine translation and the task itself. So let me find YouTube. It will be very short, just 1 minute.
They hadn't reckoned with ambiguity when they set out to use computers to translate languages. A $500,000 supercalculator, most versatile electronic brain known, translates Russian into English. Instead of mathematical wizardry, a sentence in Russian is to be fed in...
One of the first non-numerical applications of computers, it was hyped as the solution to the Cold War obsession of keeping tabs on what the Russians were doing. Claims were made that the computer would replace most human translators.
At present, of course, you're just in the experimental stage. When you go in for full-scale production, what will the capacity be?
We should be able to do about, with a modern commercial computer, about 1 to 2 million words an hour. And this will be quite an adequate speed to cope with the whole output of the Soviet Union in just a few hours computer time a week.
When do you hope to be able to achieve this speed?
If our experiments go well, then perhaps within 5 years or so.
And finally, Mr. McDaniel, does this mean the end of human translators?
I would say yes for translators of scientific and technical material, but as regards poetry and novels, no, I don't think we'll ever replace the translators of that type of material.
Mr. McDaniel, thank you very much.
So, a very, very naive way to look at the complexity of machine translation, but like with any technology, new problem, the people who start working on the problems don't immediately see all the challenges that are posed to a problem. And language is a very complex phenomenon, and translation is not a simple task. We are not there to replace anyone, and we will not be there to replace anyone also in the future, I believe. So there will be always room for it's the wrong phrasing. Machine translation systems are not there to replace anyone. They are there to assist, right? So back then, people thought that machine translation systems would be able to replace humans, but that's actually not the task that we are trying to solve with machine translation systems. And I'll show you now what are actually the main goals, as I see it, of machine translation. So the first one is to provide access to information written in a different language. You won't always have a translator by your side if you do not know a foreign language. You won't always have the resources and the money to hire a translator to translate something, some information that is not that critical, right? If you just need to know what information is provided. Like, for instance, you open a website, there's a description of a sofa that you want to buy, but it's in a different language. You will probably not hire a translator to translate that description, but you, well, if you're not very rich. If you're rich, you probably, maybe might. But realistically speaking, you will probably open an online translation engine, put in the text that is provided in the description of the sofa, and translate it using automated methods. The second goal of machine translation is to lower language barriers in communication. Imagine you are traveling abroad, you are in a village somewhere rural, in a country where no one speaks your language and you don't speak their language. It's probably very difficult to communicate if no one knows the languages. You won't also there have a translator by your side probably, but machine translation systems can help solving this issue. So there are already examples of speech-to-speech translation systems from Microsoft available, where all you need to do is just speak in your language. Your speech will be translated into different language, for instance, Chinese, and the Chinese speaker's language will be translated back into your language. The third goal of machine translation systems is to increase productivity. So none of these goals means that we are replacing anyone. We are using machine translation as an assistive technology that helps and tries to, at least in the area of human translation, machine translation systems are used to boost translation performance of translators. Any questions so far, after a little bit provocative introduction? No. So now I'll discuss about previous MT methods that we have used prior to neural machine translation, but I'll try to make it very brief so that we have time for neural machine translation. So this is a classification of the methods that have been used for machine translation. So the research started with rule-based methods. I'll talk about those in a bit. Then corpus-based methods, statistical machine translation, and the example-based machine translation methods were proposed, where instead of rules, we had to rely on data, and that allowed us to build machine translation systems for different languages much faster. And recently, since 2016, we have been using exclusively neural machine translation systems for our machine translation services. In between, when the second type of methods was proposed, people started also combining methods. So hybrid methods usually try to solve problems that any single method fails to solve properly. So when people started using statistical machine translation systems, they saw that they can still apply some rules in order to address some exception cases and thus increase translation quality. But I'm not going to talk about hybrid methods because that's like a never-ending area. So let's start about rule-based machine translation. There are three levels of how rule-based machine translation systems work, depending on how much effort we put into developing the methods. So the first and basic level is direct translation. So you have to have a let's continue. You have to have a dictionary for
Dear visitors, the library will be closing in 15 minutes.
I hope someone has the key to get out. So the first and basic level of rule-based methods is direct translation. I'll show an example further, where we use just a dictionary in order to perform translation. The next level is transfer-based machine translation, where we first analyze the source text, so a sentence. We try to figure out its syntactic structure, then transform the syntactic structure into a target language, so a syntactic structure of a sentence in the target language, and then we generate the translation. So for the transfer-based machine translation systems, we would need to have transfer rules for every translation direction that we have. And therefore, and because creating rules is actually very time-consuming, researchers also quickly started to realize that interlingua-based machine translation systems could be a better solution, where instead of creating transfer rules from a source language into a target language, we first create transfer rules from the source language to an interlingua, and then from that interlingua we have to have transfer rules to the target language. If you have 5 languages and you need to create 25 machine translation systems, so that means 25 translation or 25 translation directions. With an interlingua-based machine translation, you would need just 10, because you solve. You just need to have transfer rules from a source language into the interlingua, and if there are already transfer rules that you have created from interlingua to the specific target language, you don't have to recreate them, right? So it causes or results in much less work. So this is an example of how a dictionary-based machine translation system would work. So you have the source sentence. You would sometimes perform morphological analysis, but not necessarily. You would use a dictionary to transfer or translate each word separately. And you might use some reordering rules, which for dictionary-based or direct translation-based systems are usually pretty simple. And sometimes you would try to generate morphology, but also not necessarily. So the first machine translation system for Russian English that was presented in 1954. It was called the Georgetown experiment. That used just 6 reordering rules and very simple reordering rules to address for syntax in the translation. 6 reordering rules are nearly not enough to produce adequate translations. So this is obviously not a very good method nowadays, because no one would want to have a translation system or would be willing to use a translation system that translates, for instance, into base forms, so lemmas. And it has no notion of semantics, so lexical ambiguity with the dictionary cannot be solved. So this is a very basic method that is not used nowadays, at least for most of the languages for which researchers work on machine translation systems. So the next level of rule-based systems is transfer-based machine translation. Here is an example. So we analyze the grammatical structure of the source text. And this is the syntax tree of the source sentence. Then we transform the syntactic structure into the target language, and then we generate the translations. This is theoretically a very strong method. So it should be able to translate correctly as long as we have the correct transfer rules and we have enough data to disambiguate lexical choice. But in reality, it takes ages to actually prepare transfer rules, and often there's not enough context available also to disambiguate between different lexical choices. So this method, although very strong theoretically, practically is difficult to solve. However, it is used for languages that are close, so similar, also nowadays. So from Spanish to Catalan, there are rule-based machine translation systems available. So interlingua-based machine translation is similar to transfer-based, as I explained, but instead of direct transfer rules, you have the interlingua in between. So we'll not waste time on this here. So the next empty paradigm that was proposed was example-based machine translation. So instead of crafting translation rules, we use data and let the system learn to translate itself. So example-based machine translation is also called as translation by analogy. So first we split sentences into phrases, find phrases, those phrases that we have identified in a parallel corpus. So for instance, I have here an example, this is how it works, and I have to translate it. So I look in the parallel corpus, which is gray, the gray cylinder. I find the translations of the phrases, and then I assemble them in the translation. To identify which phrases are suitable or which phrases from the parallel corpus I have to use, the method uses tries to analyze semantic similarity, and for that it can use taggers, syntactic parsers, semantic analyzers, and various other types of resources. But it does not, so one thing that it does not do is analyze the data statistically. So it doesn't try to figure out whether this really should be translated or a phrase, this is how, should it be translated in a specific way or should it not be translated? It relies on data very heavily, and it relies on individual examples or the first examples that satisfy the similarity rules of the method. So the next type of methods that were produced or proposed were statistical machine translation methods, and statistical machine translation methods. There are various subtypes for statistical machine translation: word-based machine translation, phrase-based machine translation, syntax-based machine translation, and hierarchical phrase-based machine translation. All of those methods analyze word occurrences and phrase occurrences in parallel corpora. So we'll look at how phrase-based machine translation works. We won't look at the other methods, but you'll get an understanding of how statistical MT works with this example. So similarly to example-based machine translation, we need to have a parallel corpus. We perform statistical analysis on that parallel corpus and build several statistical models. And typical models for a phrase-based machine translation system are a translation model, which has to propose translations for phrases, a reordering model that has to be able to tell whether or how to reorder phrases such that we would acquire a correct translation, and the language model that is able to tell us whether a translation that we produce is sound in the target language and also in the domain in which we are translating the sentence into. So first, in order to build an SMT system, we identify word alignments in a parallel corpus. So we have millions, yes?
Is the short question about phrases? Are these constituent phrases, or are these phrases that you run across constituents, for example?
Those are any arbitrary n-grams that you can extract from data. So for the hierarchical phrase-based machine translation systems, you would end up with like chunks and constituent phrases. But for phrase-based machine translation systems, those can be any arbitrary phrases. And we'll see that in the next slide, actually. So the first thing we do is identify word alignments for every sentence pair that we have in our parallel corpus. And usually for SMT systems, the parallel corpus would consist of 10 to 50 million, depending on language pairs, sentences. So a lot of data. And we build a model that analyzes how often a word is or occurs together in that parallel corpus with other words. And that's basically how we build a word alignment model by analyzing word co-occurrences. When we have built the model, we align each sentence that we have in the parallel corpus, and we try to extract phrases. By extracting phrases, we build a translation model that contains, and you can see here that they are any arbitrary phrases that can be found in the sentence, usually from a unigram to a 7-gram long phrases. Also for the translation model, similarly as for words, we have co-occurrence information, how often a phrase has co-occurred together with a particular translation in the parallel corpus. And this allows us to build a statistical model that tells how probable a particular translation for a phrase is in that specific parallel corpus and that specific translation model that we get from that corpus. Yeah.
This language corpus corpora are built out of dictionaries or literary texts, or how do you do it?
After some 30 or so slides, I will answer to this question. I'll explain a bit further down. So once we have the alignment model and the translation model, we learn also a reordering model that allows us to reorder phrases. And in reality, what it actually does is it evaluates how well we have assembled a hypothesis. So if I have split a source sentence into 5 phrases, I can, and for all of those 5 phrases, I have 5 translations found in the translation model. I can assemble a translation by ordering the phrases in many different ways. And the task of a reordering model is to evaluate, have I done it correctly? Have I done the reordering of those phrases in the target language correctly or not? And here you see that when we translate from English to Latvian, there is so if I would have a phrase that is a proof and a phrase that is off context, so two phrases, those would have to be reordered in Latvian in order for the translation to be correct. So as a fourth step, we learn to recognize correct target language sentences. So we train a language model on the target side of the parallel corpus. For SMT systems, we would also use, so the language the data for language model training would often be much larger than the parallel data that we have. So that the language model is able to better evaluate sentences or hypotheses that we showed the language model. And the task of the language model is simply to tell how likely it is that a given sentence belongs to the target language. So there, for the language model, it doesn't have to know what the source language is, and it does not even have to know that we are doing machine translation, which is why statistical machine translation does not always work well, and there's only so much that we can achieve with statistical machine translation, because all of the models are independent. They are not a unified model that analyzes the whole sentence. So we analyze n-grams, we don't analyze the whole sentence. We assemble a translation using a translation model. We reorder the phrases by not knowing what source text or how it should be translated. The reordering actually for phrase-based machine translation also has nothing, it doesn't know syntax. The only thing is, that it is able to do is learn syntax, but it is not able to learn long distance dependencies. So for instance, if you have to reorder something from the very beginning to the very end, switch the first and the last word, for instance, in order to get a translation, it would be very difficult for an SMT system, or if not impossible, to do it. And also because we are working with phrases, sometimes it happens that, and each of those models is n-gram based, it can be that there's a lot of morphological disagreements between words. So you would have the cases wrong or genders wrong, etc. So it could be also that during the translation itself, so if the sentence is very long, you would start with one meaning, and then you would end with a different meaning, even if it's the same word or the same gender or number that is described or written. So here is an example of how a language model should work. For instance, we give a language model a hypothesis. So this is a very suitable sentence for the example, and the language model has to tell that, well, it's a good sentence in the target language. It does not see the source text at all. And if we give it a bad sentence, for instance, this is a much suiting sentence for an example. So you can probably tell the mistakes in the sentence. It should be able to tell us that that's a bad translation, and it should have a lower score assigned. So before we dive into neural machine translation, I also want to spend a minute or two on how we evaluate machine translation systems, so that because further in the slides I'll have graphs that have scores. So there are an abundance of evaluation methods, automatic evaluation methods that can be used to evaluate machine translation systems. Some 5 years ago, I heard a number, or saw a number in a presentation at a conference, that there were 70 or so evaluation methods available for machine translation. There's an annual evaluation task, shared task, on where people, researchers, develop methods for evaluation of machine translation systems. So the number of proposed methods increases almost on a yearly basis. But there is one method that almost everyone uses. The scientific community itself doesn't think that it's a very good method, but if we analyze enough sentences and look at the result as a whole, so for a single system, then the results of this automatic evaluation method correlate pretty much similarly to other methods, and also for when we translate into English, it correlates almost better as other methods with human judgments. So the method is called BLUE, Bilingual Evaluation Under Study. What BLUE does is it measures the n-gram overlap between an empty hypothesis, so it's a translation produced by a machine translation system, and a human reference. So when we translate when we evaluate machine translation systems, we always have a test set. A test set is a data set that has sentences and their human translations available. There are usually 1,000 to 2,000 sentences in a test set. And if the test set is good, it will represent the domain that needs to be evaluated and various types of text that need to be evaluated. BLUE calculates, so when we show BLUE a machine translation suggestion and the true reference, so the human translation, it calculates the precision of n-grams that are found within the machine translation hypothesis and the reference. So how many of n-grams that are in the machine translation output are correct translations. So the score is averaged out over unigrams, bigrams, trigrams, and 4grams. So BLUE analyzes the content overlap for up to 4 tokens. And it tries to penalize situations where the hypothesis is shorter than the reference itself. So there's a brevity penalty that lowers the score if the hypothesis is shorter than it should be. Any questions so far? No. So then I'll quickly also describe what we do in Tilde before I switch over to neural machine translation. So Tilde develops a wide variety of language technologies, of which machine translation is just one type of technologies. Tilde develops also speech recognition and synthesis solutions for Latvian and Lithuanian. Virtual assistants, for those who are from Latvia, you've probably heard in the news about Tilde virtual assistants, and also natural language processing tools for Latvian and Lithuanian. So gram checkers, spell checkers, dictionaries, etc. In terms of machine translation, Tilde does active research and also provides machine translation services to enterprises. So companies that usually work on language in the language sector. So, for instance, translation agencies, also international companies that operate in multiple markets and need to translate content between different languages. So we have a platform which is called Tilde MT, where we train machine translation systems on customer data, and then we deploy the systems throughout the interfaces that each customer requires. If you are a translator, you probably use computer-assisted translation tools, and Tilde MT has interfaces and plugins also for the most popular computer-assisted translation tools. Within our research activities, we take part annually in an international competition where we compare how good our methods are with the competition and researchers across the globe. So the competition is organized within the scope of the Conference on Machine Translation, an annual conference. And within that conference, there are several shared tasks. One of the shared tasks is the metric task that I briefly mentioned earlier. But there are also translation tasks where participants have to develop machine translation systems using data that the organizers provide, or data that participants can acquire themselves also. And then submit, when the systems are ready, submit translations to the organizers, and the organizers organize then a human evaluation effort where every system is evaluated. And then at the conference, which this year will happen next week in Italy, the official results are announced, so who achieved the best translation results. We do not participate in all the shared tasks for all the language pairs, but in each year, so we have participated in the last 3 years, 2017 through 19. We've participated because the shared task involved also Baltic languages. So English Latvian in 2017, English Estonian in 2018, and this year English Lithuanian. So we submitted, developed systems and submitted translations, and each of those years, so in 2017, here you see official results from the shared task. On the vertical axis, you will see the human evaluation. So the higher the score, the better the systems are ranked by human evaluators. And the human evaluators are professional translators, language experts. And on the horizontal axis, you'll see automatic evaluation scores, so the blue scores, which are calculated automatically. If we talk about neural machine translation methods, the blue scores do not necessarily correlate with the human evaluation scores, but the human evaluation scores are considered the scores that are trusted. So places or who won or who lost are assigned based on the human evaluation scores. So these are the results for English Latvian. So last year we participated for English Estonian, and this year we have been participating for English Lithuanian, and these are yet unofficial results that will be available next week. So you see that we are for the language pairs that we cover, we are competing with other participants. So this year we've competed with Microsoft and last year we competed with a Japanese research institute. So the NICT is a research institute from Japan. And in 2017, we competed with Google. So that brings us to our actual topic, so neural machine translation. So I'll start with introducing you to neural networks. I have heard that you have heard something today or earlier about neural networks maybe, or at least some areas of neural networks. So if I'm talking about basic things, raise your hand and say move on. So here you see an example of how a neural network looks like for machine translation. So machine translation is a sequence generation task. So we have an input sequence as words in a sentence. So a sentence consists of one or more words, which constitute a sequence. And the translation also consists of one or more words, which also is a sequence. So the task of a neural machine translation model is to analyze the source sequence, encode it, and then decode the source sequence into a target sequence. And we'll look at how this works in the next couple of slides. So this architecture is, we are not actually currently using it, but it was state-of-the-art till 2017, but it's very good for explanation purposes, therefore we'll use it in this talk. So what are neural networks? I'm not sure what you have heard, but neural networks are mathematical models that allow to store artificial intelligence. Here you see an example of how a neural network might look like. So there's an input layer where the neural network receives input signals. There is a hidden layer or multiple hidden layers, and an output layer where when the signal is passed through the neural network, it produces some output. And it could be that it produces the output in one signal or many signals, depending on what the neural network does. The neural network, or each layer of the neural network consists of one or many neurons, and each neuron is able to analyze input signals, and based on what it receives in the input signals, it is able to decide whether it needs to emit an output signal itself. So intuitively, if we think about artificial neurons, they work similarly to natural neurons. So there are input signals, so and the each neuron receives input signals, and based on what or where the signals came from and how strong the signals are, it is able to decide whether to emit this signal further. Practically, how it looks like, here you see an example of how an artificial neuron looks like. So there can be input signals from other neurons, or if it's the first layer of a neural network, then the input signal comes from outside. The input signals can come from one or many different sources. Each of those signals is analyzed by the neuron, so it is multiplied by a parameter, so it can be downgraded or upgraded based on what the parameters are. all the signals are accumulated into one, I would say, large signal. So that's what the transfer function does. So it sums all the signals, weighted signals together. And then the neural network decides, using an activation function, whether it should emit a signal or not. So a bit mathematical. But to put it in simpler words, or if you try to think about how it works, think about signals. So there are inputs. If a neuron receives input signals, based on what the signals or how strong the signals are, the neuron decides whether it should emit a signal or not, and how strong the emitted signal should be. When we assemble the neurons one after another through multiple layers, we can create a complex network that is able to traverse a signal through the entire neural network. And based on what the input signal is, the neural network can learn to do many complex things. And one of those complex things is machine translation. How do we train a neural network? There's a method which is called backpropagation. It is called a trial and error method that works as follows. So we have an input sentence, so a source sentence that needs to be translated. When we are training the network, we start with a network that does not know anything. So if we show it an input sentence, it will produce some garbage. So a neural network is able to produce a result irrespective of whether it's trained or not. So when we assemble a neural network, so we create this architecture of a neural network, it is already ready to go. So we can already start using it. But if we haven't shown it any data, if we haven't taught it, so the correct parameters, how to weigh each input signal, it won't know anything. So it will produce garbage, but it will be able to produce garbage. So the task of training is to make the neural network learn not to produce garbage, but to produce what we expect it to do. So, and this works as follows. So we show the network an input signal. So the input signal in our case is a sentence. We let the neural network traverse the signal through the network and produce a prediction. So if we receive an input sentence here, the neural network will produce a hypothesis, so a translation on the output side. Then we compare what the neural network produced with what is in our reference. So we train a neural network for neural machine translation with a parallel corpus, so we always have the correct translation for each sentence. And if the translation is not correct, we adjust the parameters of the neural network. So the parameters of the neural network are the parameters that are stored for each neuron. So, as I said, each neuron receives input signals from other neurons that are before it in the neural network, and it weighs the signal using parameters. So all the knowledge that a neural network can store is comprised of the parameters that make up a neuron and how each neuron is connected to each other neuron through the neural network. As difficult as it may sound, this allows to store very complex knowledge. And knowledge that is, for our case, necessary to perform translation. So here you see on the bottom side how a neural network is trained. So when it has not seen anything, the quality of the neural network is very low. But once we start showing it sentences, the quality starts to increase. At first, it increases rapidly because it is able, well, at least this, with this method that we use, it is able to learn rapidly to produce almost correct translations. And then once we have shown the neural network quite a lot of sentences, the increase of quality flattens out. So we don't see a linear increase of quality, but it's faster at the beginning and then very slow. On the other axis, we actually see the error. So the difference between the prediction and the correct translation. And the error, when we train the neural network, has to decrease. So we see that it drops when we start training a machine translation system, and the loss also flattens out. So the more sentences we show it, the better it becomes. And here you see that for this neural network that we've trained, this is a graph from a Lithuanian English machine translation that we trained for this year's shared task on news translation. So it saw 300 million, almost 300 million sentences before it stopped training. The data set that we used did not consist of 300 million sentences. It consisted of, if I'm not mistaken, 30 or 40 million sentences. So that means that when we show a neural network a sentence, we go through all the data set and then we start again. We shuffle the data set so that the neural network doesn't learn the sequence of the data that we show it. And we continue showing it sentences from the same data set. The more we show it, the better it becomes, up to a certain point. So how, an obvious question you probably ask yourselves is, how do we pass a text into a mathematical model? So here we can't actually multiply a word with a decimal number. So school times 0.1 would not make any sense. So this is why we need to figure out a way how to pass or transform text into a numerical form, such that it would allow us to feed the neural network, and when it produces an output, we would be able to figure out from a numerical form in the output what word it actually belongs to. So the solution for our case is to use one-hot vectors, and it's probably similar to other natural language processing tasks, where each word in a dictionary corresponds to a certain position. So here you see an example of a dictionary. This is a dictionary. It consists of 5 tokens. Each of the tokens has an index, a position in the dictionary. A one-hot vector looks, if you have a word, it looks up the word in the dictionary and produces a vector which has zeros except for the position where the word is in the dictionary. So, for instance, for the word dictionary, the one-hot vector is 0, 0, 0, 1, 0, because dictionary was in the position 4 in the dictionary. Yeah. So we can convert every word to a numerical form using one-hot vectors. And we do this in neural machine translation and also other NLP tasks. So one thing about neural networks that I have not told you is that they expect that there will always be a fixed input, the input signal will be of a fixed size. So if I have pass a neural network or build a neural network such that it can accept a vector of length 5, so a 5-dimensional vector. A 5-dimensional vector means that there are 5 input signals, so just 5 numbers. I cannot just arbitrarily decide to use 6, a vector of size 6 or 7 if I stumble upon new words. So the length is fixed. So there's also another issue that neural network-based methods usually require very large computing resources, and if the input vector is too large, then we might not have enough computing power to train such a network or store the network in the memory. So typically, neural machine translation models that we train use 4 to 1,000, so 4,000 to 1,000 dimensional vectors in the input signal and the output signal. However, when we train an English-Latvian, for instance, neural machine translation system, there are over 400,000 unique tokens on the English side and over 1 million tokens on the Latvian side. So Latvian is a bit more morphologically rich, so there are more inflected forms, and that brings the number much higher. Obviously, if we would just take the first 100,000 or for the current systems that we train, we usually use 25,000 dimensional input signals. That would mean that we would not be able to translate most of the words that are there in the data set, and that's not acceptable, right? So what we have to do then, in order to be able to produce a fixed size input vector, is to split each word down to subword units, such that the amount of subword units would be identical to the size, so the dimensionality of the input signal. If we talk about language, think about we need to split words, for instance, into morphemes, right? In neural machine translation, we don't do this, but to make it easier to understand, think about if we would split the words down into morphemes. What that would do is it would lower the number of different unique parts that we have to store in a dictionary, and it would allow us to squeeze the whole vocabulary down into a smaller vocabulary. In neural machine translation system, instead of splitting words into morphemes, we use a statistical method, which comes from text compression world. It is called byte pair encoding. And this method works as follows. So we first split all the words in characters. So all the words that we have in our data set, we split into characters. Here you see an example. So this word doesn't make any sense, but imagine that it's a valid word. We split it into characters, so the underscores represent a space. Then we count bigrams in our data set, so all corpus. We count each of those bigrams, and we merge the first or the most occurring bigram together. So this produces one merge operation. Then we look at how many merge operations we have already produced. So after the first one, we have only one. If we have stumbled upon the maximum number of merge operations, so the maximum number is the amount of input signals that we want to have in the neural network as input, so how large the input vocabulary should be. If the merge operations have not reached the maximum count, we continue by counting bigrams. So if we have merged two characters, they produce another token, which can then be used in a bigram together with a different token. So we count again, merge again, and we continue till we reach the maximum amount of merge operations. So this is a technique that allows us to split words, but we can always see where the split has been made. So we don't lose any information by doing this. Although this is very statistical, it has nothing to do with linguistics. It analyzes just counts of bigrams in the dataset. What it does is it splits rare words down to smaller parts, but it keeps frequent words unsplit, because the merge operations will learn that frequent words should not be split. So for instance, here you see an example from an English-Lithuanian NMT system that we trained recently. I have an input sentence. This example shows how many words are split in the best English-Lithuanian NMT system of 2019 by byte pair encoding when using 25,000 merge operations. And after splitting, I see that most of the words are not split down into smaller parts, and this is because they are very frequent in the dataset. If they are frequent, we don't want them to be split, and this allows us to both reduce sparsity in the dataset, because now we don't have 1 million words, we have just 25,000 parts, and it allows us, or for the neural network, to treat very frequent words specially, differently from the other words. So here in this example, the only thing, the words that were split were NMT, so an acronym, byte, probably a rare word in the dataset, encoding, and 25,000. Which is very common because numbers are rare in data, except for years, which are very common. So now that we know how text is squeezed into a fixed vocabulary and how words are vectorized, let's look at how an NMT model works. So up to now, we have learned or we have talked about how neural networks work. We have talked about how we feed data into a neural network, so how we feed text into a neural network. But we haven't actually talked about neural machine translation models. So we'll use this example, which is an encoder. So an encoder and decoder-based model. The encoder's task is to analyze the text, the sentence, and produce an internal representation of the sentence. And by internal, I mean we don't actually know and don't see what happens in the neural network. The architecture of the neural network forces it to learn a representation of the sentence within the neural network. And then from that internal representation, it decodes and produces a translation. And now let's see how that works. So when we have, so the first step is to transform all words into one-hot vectors. That we already covered. Then we project words into a multidimensional space, which is also an embedding space. So different from other natural language processing tasks like named entity recognition, sentiment analysis, etc. We don't use pre-trained embedding models in neural machine translation up till this year, but previously we have not used them simply because GLOVE or word-to-vec are not useful for machine translation. And this is because the task of, for instance, word-to-vec is to put words that occur in similar contexts closer together, but that's not a task that is helpful for machine translation. For machine translation, we need to put words that are synonyms closer together. And that does not always mean that they occur in similar contexts. For instance, Latvia and Russia should not be placed very close together, because in the translation we don't want Latvia to be confused with Russia or Greece or Spain or any type of such entities. The neural network architecture that we use learns word embeddings itself. So it learns from data what are important embeddings for machine translation. If we talk about word embeddings, let's try to picture how word embeddings should look like. For instance, if we have 3 words, blue, red, and rose, or rosé, how would you arrange the words on a plane to satisfy similarity? The task of embedding, word embedding, is to place a word in a multidimensional space. So to place it, if we have a 2-dimensional space, that means placing the words on a plane. So if we have 3 words, the task of embedding is to figure out where to put them. So there are multiple ways how we could, as humans, approach this task. So we could use as similarity, for instance, morphological similarity. We know that red and blue are adjectives, and here sky, instead of rose I have sky here. Sky is a noun. So those 2, red and blue, should be closer together, but sky should be maybe a bit further away. We could try to approach a different method, so semantic similarity. So instead of having sky very far, sky is blue, we know that, blue is also blue. Maybe those should be put together closer. So there is no such one thing as one similarity. It may depend on what the task at hand is, and all we know is that similar words should be closer together. If we have more words, we actually have a problem that we cannot put them on a plane anymore. So if we have 4 words, in order to correctly position distances, we would need to introduce a 3rd dimension. And to combine like morphological similarity and semantic similarity, we also need to add more dimensions. So we can actually have both these similarities, so morphological and semantic similarity, in one embedding space, but a multi-dimensional embedding space. So instead of having a plane, we could have additional 2 dimensions. So that would bring us to 4, and we would be able to place all the words such that morphological similarity does not interfere with that semantic similarity. So usually in neural machine translation and in other tasks, the embedding layers consist of 512 or 1024 dimensions. So for us, imagining or picturing 2 dimensions is easy. Imagining a bit more, so 512 times more dimensions is a bit more difficult. But the task of embedding is to figure out what is similar based on the data itself and the task at hand. So for machine translation, that is why we don't use those word-to-vec embeddings or GLOVE embeddings, but trained embeddings for the task itself. So the task is neural machine translation and not to predict which words are closer together in a context. We can apply this embedding method also for full sentences, not just words themselves, and we'll see that later on. So once we have trained a neural network, we can visualize the embedding space using visualization methods. So here you see that I have visualized the embedding space of Latvian English neural machine translation system. So the tool that I used is called Tensor Projector, and it's something that Google's researchers have produced. It's available online. You just need to upload data from your embedding space, and then it will analyze. So squeeze the embedding space, in my case, down from 512 dimensions down to 3 dimensions. And it will figure out which properties in the multidimensional space are important and distinguish or show similarity. So here you see that, so for those who know Latvian, debates, diskusijas, apspriež, those are sort of similar words. Or here on the right, sēde, sēdes are different inflected forms of the same word. I don't have it here, but an interesting phenomenon that we can observe when training embeddings for neural machine translation systems is that it will align numbers, especially years, in a sequential order. So you will see every year perfectly aligned one after another in the space, such that you can traverse through all years that are in the dataset. Something similar happens also for months, but I don't have it pictured here in this example. So now that we have projected or embedded each word, we need to pass each word in a sequence one by one through a recurrent layer. So a recurrent layer is a type of node in a neural network, or a layer in a neural network that has the same parameters for each connection. So it has the same parameters regardless of the time position. So here in let's go back to the neural network. Here I showed that each of those connections has a parameter from one neuron to another neuron. In a recurrent neural network, you would have a layer that repeats multiple times, and the same input parameters are used in every position that comes. So imagine that we have an input word. This represents an input word, so a vector of 3 dimensions. So 3 individual input signals. If I want to pass the next word to the neural network, I would have another 3 neurons, so down here, and I would have connections from those three neurons to an identical setup of neurons as for the first word, with the same parameters. And I would have connections from the first word's hidden layer, so the recurrent layer, to the current word's hidden layer, in order to pass on information from each previous word to the next word. So I'm not sure whether it made sense. So imagine it like this. So we have an embedding for the first word, so a vector for each for the first word. We pass the signal of the first word to the recurrent layer. The signal is processed, so the neural network decides whether to emit a new signal to the next layer, and it does so. It emits a signal to the right here, to the next time step. The next time step after the first time step is the second time step, when the second word is passed to the neural network. So we pass the second word's embedding space to the recurrent layer, which receives input signal from the previous word, accumulates it, decides whether to pass the signal on and how strong the signal should be, and does it so for all words that are in the sentence. So from left to right, we accumulate the signals from the embeddings that we got from left to right for each word. So at the end, we get a vector here. So just this first, these 3 tiles. Imagine it's a 3-dimensional vector that accumulates or contains the whole meaning of the sentence within itself, from left to right, encoded into one vector. We do this also in a reverse direction, so from right to left. We reach also a position, so the last step where we have the meaning of the whole sentence encoded from the right to the left in one vector. If we combine each of those vectors together, so the left to right and right to left vectors together, at each position in this network, we have the whole information or the knowledge about the whole sentence. So in the second position, we have the signal that comes from the first word, the signal that comes from the current word, word's embedding, and we have the accumulated signal from all the further or next words in the sentence. So this is a recurrent layer. What it does is encodes the sentence into an internal representation. Once we have the internal representation, we can actually picture it. Imagine that these networks, these vectors here and here contain the whole meaning of the sentence within one vector. similarly as words, we can acquire for every sentence that we have in a data set these vectors, and we can then plot them in a three-dimensional space, and we can see what happens. So what happens is that similar sentences are placed closer together. So here, for instance, we have vai jūs runājat angliski, do you speak English, in a formal way, and vai tu runā angliski in an informal way. Actually, if you would translate this into English, they would translate into the same. Yeah, the same sentence. They would translate into do you speak English? Because the task is machine translation puts closer together sentences that are translated similarly or the same. All the other sentences that have been marked as very similar, so I selected this sentence, and the tool, so tensor projector, showed me which sentences in my dataset are similar to this sentence, do you have a house? All the sentences that we see are questions, right? So we don't see any other type of sentence. However, they are not necessarily the same. There is distance between the sentences, and the longer the distance is, the less similar they are. So the fact that they are marked does not mean that they are very similar. Yeah, they are just the most similar sentences that I had in that small data set that I had. But this is a very good example, so do you speak English? So that we can acquire by encoding the whole sentence. The meaning of the whole sentence is squeezed into one vector. So once the encoder has completed its task, we use a decoder, which has to generate words. The task of the decoder is to take as input the signal from the encoder, so that it's not very clearly visible, but that's not that's okay. It takes as input the signal from the encoder, and then it has to decide what to produce in each time step. So starting from left to right, which words to produce in the translation. So that's the task of the decoder. We use in our decoders an attention mechanism, which actually accumulates all the signals from all time steps. So all individual encoded positions. So the hidden layers representation from the first word, second word, third, fourth, and etc. So it accumulates the signals using an attention mechanism. The task of the attention mechanism, so accumulates means it creates actually one vector out of many different vectors, just combines them into one. The way how it does it, it tries to figure out which position is important for the current word that we have to decode. So we have to generate in the translation. So imagine we have a sentence after encoding, etc. If I start decoding the sentence, I would probably start looking at the first word, because in Latvian I would say pēc, so after. If I would want to decode pēc, the attention mechanism will say pay attention to the first time step. This is important because in our practical applications, we do document, so support document translation. Documents contain formatting tags. Also, if you're a translator and use a computer-assisted translation tool, there are formatting tags in segments in order to figure out which word, for instance, is marked in bold, italic, etc., which span has a hyperlink added. We need to know which word in the source corresponds to a word in a translation. So we need to have the alignments from source to the target. And the attention mechanism, because it pays attention to what is important when we decode a certain word, can be used to acquire those alignments. So once we have the accumulated vector, which pays attention to the important part of the network, we pass it through to the recurrent layer of the decoder. So this is not a bidirectional recurrent layer, it's a one-directional recurrent layer because we have to produce a translation from left to right. In the first position, we just use this information and try to guess, well, the neural network guesses what the output should be, so what the first word or word part should be in the translation. Once it has produced the first word, it sends the signal back to the recurrent layer. I have produced this word in the translation. Know this for further time steps. So when we have to decode the second word, we know that the neural network has produced paths for after encoding. So we know what the neural network has produced, and we ask the attention mechanism show us what is the important time step in the encoder that I have to pay attention to when decoding and when producing the translation of the second word. This we do till we stumble upon a token that says end of sentence. So when we stumble upon end of sentence, the neural network stops translating. So that is how neural machine translation works, and it's 6 o'clock. And I have not told you how we develop machine translation systems. But we can stop here if we have to. Depends on you. What? I can quickly browse. I will probably send the slides so that they are available to everyone. What comes further is less interesting. So the most important things about how neural machine translation works, I explained to you. The further shows how we develop systems, how we train, where we get the data from. So there's a workflow that we use. We acquire data from different sources. Usually there's a lot of data that we can use. Depends on the language pairs. Then an interesting thing if you want to imagine how much data that is, if a single translator would translate, you would need 182 to 372 approximately years for one neural machine translation system. A lot. So data comes in different forms and shapes. In order to train a system, we format it into one single format. So if you are working on language technologies, then you probably have some data management processes intact, or how your data is managed. So it's the same in machine translation. If you work with customers, then it becomes much more complex because customers have many different types of formats that they use. Then we pre-process the data, and pre-processing allows us to reduce noise, reduce data sparsity, enrich data with external knowledge like linguistic information if we use parsers or taggers or morphological analyzers. We split data into smaller chunks because when we pass data to a program or send a sentence to a program, all it sees is bytes or bits. We first need to figure out or inform the program that these sets of, or this sequence of bits, please analyze as one single unit. So we need to figure out what those single units are. And the whole process for document translation in Tilde looks like this. And the first part is pre-processing, and each task has its job in order to either split the data, reduce noise, reduce sparsity, or enrich the data in some specific way. But if you want to start working or doing something in this area, the whole workflow is not necessary. So the simple workflow for machine translation would mean that you would tokenize text. If you would translate, you would split sentences. Then you would true case the text, split the words using byte pair encoding, train a model, and then, or if the workflow is translation, you would perform translation, and after translation you would perform the opposite. So if you have pre-processed data somehow, you need to make sure that you reprocess it back to the original form, how it was. So if you separated tokens, so a space from a comma from a word with a space, after a translation you need to remove the space. It's the same with all the different processes that occur. If you true case a word, so transform the word from its writing in the text into its canonical writing in terms of character registers, you need to put the registers, character registers back, so either uppercase or lowercase. Then we do also data filtering, so data that we get is always noisy. Don't assume that your data is clean. If you work with machine translation, data is always noisy and it's important to clean it. And it's also important to normalize it. So, for instance, here I have examples that data can have different punctuations. There can be issues that occur because of optical character recognition if data comes from PDFs, and etc. So many different issues can be apparent. And then also you have to apply standard natural language processing pipelines like tokenization, sentence splitting, etc. That's it. And then you train a model, the one that looks like I showed and described you in this talk. And that's it. At the end of the presentation, I have also listed some neural machine translation tools and what is required to actually train a neural machine translation model. You can't do it on laptops like this because you need a graphical processing unit, so a video card that is capable of calculating a lot of data. Yeah. That's it. Thank you. Maybe there are some questions that I didn't answer. Yeah.
One question on the language models. You mentioned it in the beginning that one is long distance dependencies and secondly the subject verb agreement maybe not the hardest. But if you go from the Estonian, for example, to English pronouns, somebody who's going to have one pronoun and forward in your sheet. How do you is it possible? So how will that fit into a model like this?
So in neural machine translation, we don't use language models. at all. So all the translation is performed by just the single neural network-based model, and it learns to produce hopefully correct translations from the data itself. So as long as what you want to get in a translation is in the data, the neural network will learn to produce it.
So
there is no language model in the neural network, no.
You probably won't get, let's say, license agreement also.
It will be discovered by the and the fact that that the network sees the whole sentence, it actually knows or has the ability to know where the agreements are if the data allows it to learn it. So if the data has examples of such cases where you need to pay attention to where are long distance dependencies, the network will learn it. Yeah. So this is one reason why neural network-based methods are so strong over statistical methods. They use one model that is able to observe the whole context and not just bits of the context in n-gram form, not everything as one. Yeah.
But it wouldn't look like the evaluators you have, which scope by an n-gram variation, let's say a quadgram, for example, would be able to detect wrong lines.
Yeah, so automatic evaluation methods are biased towards statistical methods. That is why I mentioned in the beginning that also in the shared task on the conference on machine translation, the main evaluation method is human evaluation, so human judgments, and not automatic evaluation. And the automatic methods are not that reliable for neural network-based methods, and they are not reliable if you compare systems of different empty paradigms. So they are biased towards statistical machine translation and will always score statistical machine translation systems higher than they actually are. It was also the case with rule-based machine translation systems. So when statistical machine translation systems were introduced for English-Russian and Russian-English, there was a company, if I'm not mistaken, Prompt, that had a very strong rule-based machine translation system and participated every year in the shared tasks and won, but they had a very low automatic evaluation score. So Blue and all the other methods that favor statistical machine translation systems scored rule-based systems lower. And it's the same now for neural machine translation systems. So if you compare different empty paradigms, then automatic methods should be, you should approach this carefully. Sometimes they work, but sometimes not.
A small question about the sequential alignment of years in embedding. How do you explain that?
I don't. I actually, it's something that the network learns from the data. I have not analyzed why that happens, but it's an interesting phenomenon. It's like you've probably, if you have seen lectures on word embedding, someone probably has showed you embedding mathematics, where if you take away from a word a different word and add a different. Yeah. So this actually is a theoretical example which in many cases does not work, but the data itself has allowed the network to learn this phenomenon. And for numbers, and I guess it's ability of the network. We don't know. That's also one thing why neural networks are sometimes called black box methods. You don't see what's inside and how it's inside. We make predictions or we make guesses of what's inside the neural networks. There are methods that allow us to test whether the neural networks learn something, for instance, some grammatical structures, whether they learn to recognize or handle grammatical structures also in machine translation. But those are also guesses towards what happens in the neural network. Yeah.
Did I understand correctly that in the training you put 30-40 million of data several times? Why is one time not enough?
Because it's how the network learns. So by showing it just one example, it won't be able to learn how to produce a correct translation. When you show it similar cases multiple times, it will learn to produce correct translations. But when you show, so you show a network a sentence, and after that you show a different sentence. When you show the different sentence, it will adjust the scores towards that different sentence. So it will probably lose ability to translate the previous sentence in the same way how you want it to translate. So by showing the network more and more examples, it arranges the parameters such that it can handle the whole data set better. Yeah.
Remix it.
Yeah, you remix it, and depending on the data set, it could be, and also on the language. It could be that for some language pairs you don't need to show that many times sentences. If the language is very broad, like the general domain systems that we produce and train for public consumption, so the systems that we put online and in our services, those that are where we don't know what data people will translate, those are trained on very broad domain data, and which varies a lot. So if I show the data, like the first part, the first part of the data, and then the second part of the data, it will forget to translate the first part of the data. So we mix it all the time so that it arranges the parameters such that it knows how to handle everything, or is able to handle everything better. So it generalizes the model by mixing and showing the same over and over again. But it's not necessarily the same. It's just the data, we have it so much, like 40 million and not more. If we would have 400 million sentences, maybe it would be enough to show it everything just once, and it would learn to generalize within those 400 million sentences. But we don't have that large data sets. I don't even know whether there is, for any language, that large data set. I have not heard. Maybe somewhere hidden behind Google's doors, or I don't know. Yeah. Did this answer the question? No.
Thank you, Mārcis.